Imagine you're going in for like a totally routine surgery.
Yeah.
Nothing overly complex.
Right, just a standard procedure.
Yeah, exactly. So the anesthesiologist gives you this everyday standard muscle relaxant just to help secure your airway. I mean, it's a drug they give to thousands of people every single day.
Oh, absolutely. Very common.
But then instead of wearing off in a few minutes so you can, breathe on your own again, the drug just lingers. Your
Yeah.
muscles stay completely paralyzed.
Which is terrifying.
Yeah. You develop fatal apnea, and suddenly the whole medical team has to scramble just to keep you alive on a ventilator. And the craziest part, the cause of this catastrophic failure isn't like a dosing mistake or a surgical error.
No, not at all.
It's just this completely silent, invisible variance in one single genetic enzyme that you had literally no idea you were carrying.
I mean, that scenario right there is the absolute perfect illustration of why physiological chemistry isn't just, academic trivia. You can't visually see that genetic variance on an X-ray or an MRI.
Right.
The patient looks perfectly healthy. But on a molecular level, they're just missing the specific biochemical cleanup crew that's required to process that drug.
Which brings us to the mission for today's deep dive. We are cracking open the 4th edition of Principles of Medical Biochemistry by Gerhard Meisenberg and William H. Simmons.
A classic.
It is. And, the authors actually joke in the preface that biochemistry is notoriously a cause of pre-traumatic stress disorder for medical students.
I can definitely vouch for that. It is dense.
Yeah, I mean, the textbook is this massive landscape of shifting invisible molecules, but our goal today is to kind of cut through all those abstract theories and extract the actual physiological chemistry that bridges the gap between, microscopic molecules and real-world clinical medicine.
Because the clinical application is really where this material comes alive for you as a learner. We aren't just going to spend time memorizing abstract pathways today.
No, definitely not.
We're focusing strictly on the mechanics of survival. But before we get into the systemic failures, I think we have to establish the physical baseline of the human body, right? How it literally funds its own internal construction.
Yeah, let's start with the literal building block. So if you take a standard 75-kilogram adult, the structural composition is overwhelmingly water. It's like almost 2/3 of the total body mass.
Right. It acts as the universal solvent for all these biochemical reactions.
Exactly. But looking past the water, the solid mass is heavily dominated by two really distinct categories, which are proteins and triglycerides.
Yeah, and those triglycerides, they serve as the primary storage form of metabolic energy. They're sequestered away in your adipose tissue. Basically, they are the long-term reserves.
The savings account.
Exactly. And the proteins, meanwhile, they form both the structural scaffolding of the tissues and the actual cellular machinery itself. I mean, they are the enzymes, the transporters, the contractile elements in your muscles.
But to keep all that machinery running, building new tissues and just maintaining cellular homeostasis, that requires massive amounts of energy. And the currency the body uses to pay for all that work is ATP, right? Adenosine triphosphate.
Yeah, ATP, we hear it referred to as the energy currency all the time, but the mechanism behind how it actually stores that energy is, well, that's what's really fascinating.
It's not just magic.
No, it comes down to two specific, highly reactive bonds. I'm talking about the phosphoanhydride bonds.
Right, because ATP has those 3 phosphate groups strung together.
Exactly. And the bonds connecting the second and third phosphate groups are essentially functioning like coiled springs. You have to remember, phosphate groups carry negative charges.
And negatively charged molecules strongly repel each other.
Like magnets. So forcing them together into a chemical bond requires a massive input of energy.
So the cell is basically compressing this molecular spring, and then when an enzyme comes along and cleaves off that terminal phosphate group, the spring just snaps open.
Yeah, and it releases this huge burst of kinetic energy. And that burst of energy is utilized to drive anabolic pathways.
The builders.
Right, the synthetic processes where the cell builds larger, more complex molecules like proteins or glycogen. The body maintains this continuous, delicate flux.
It's a balance.
Exactly. Anabolic pathways consume ATP to build macromolecules, while catabolic pathways break down dietary nutrients or stored reserves to generate more ATP. And under normal physiological conditions, these synthetic and degradative rates are, tightly regulated to match each other perfectly.
Which makes total sense until you look at what happens when that balance physically breaks down.
Right.
Like if a patient inherits a genetic deficiency in just one of the enzymes responsible for a catabolic pathway, the breakdown machinery just jams up. But the synthetic pathways, they're still churning out material.
They don't know to stop. So the mechanical result is basically a massive traffic jam at the cellular level.
Oh.
Because the degradative assembly line is halted, the intermediate molecules, or the undegraded macromolecules, they have nowhere to go. They literally begin to accumulate inside the cell.
And they can't just stay dissolved, right?
No, eventually they precipitate out of solution and form these massive toxic deposits.
Hmm.
This mechanism is the entire basis for storage diseases. The cell physically swells and chokes on its own biological backlog, which eventually leads to tissue necrosis and organ failure.
That is wild. The
Yeah.
breakdown machinery being just as critical as the synthetic machinery really brings us right back to that scenario we opened with. Because sometimes an enzyme deficiency doesn't cause a massive backlog that kills the cell.
Right.
Sometimes it just sits there, completely dormant, until modern medicine introduces a foreign molecule. So let's look closer at that succinylcholine case.
Yeah, succinylcholine. It's a short-acting depolarizing muscle relaxant. In a typical sequence for general anesthesia, it's given to induce temporary paralysis, which allows the medical team to intubate the patient.
And its main utility is that it's super brief, right?
Exactly. Its utility comes entirely from its brevity. Once injected, it binds to receptors at the neuromuscular junction, causes a brief contraction, and then completely blocks further signaling. And normally it's rapidly hydrolyzed, meaning it's broken down by water, by an enzyme circulating in the blood called plasma cholinesterase.
Okay, so the plasma cholinesterase is basically just floating in the bloodstream, bumping into the succinylcholine molecules and mechanically tearing them apart. So the paralysis wears off in a matter of minutes.
Right, the kinetics are incredibly fast. But approximately 1 in 300 individuals carries an atypical variant of the gene encoding plasma cholinesterase.
Wait, I want to pause on the statistical weight of that.
Uh,
1 in 300 people. That is a massive portion of the population.
it really is.
And because this specific enzyme isn't tied to processing daily nutrients or like clearing cellular waste, these people walk around completely asymptomatic. They have zero clinical indicators that they're carrying this variant.
None. They are perfectly healthy until they are lying on an operating table. When a standard weight-based dose of succinylcholine is administered to one of these patients, the reduced efficiency of their plasma cholinesterase means the drug just remains active at the neuromuscular junction for a highly prolonged period.
So instead of a few minutes of relaxation.
The patient experiences prolonged respiratory paralysis. And if the medical team is not prepared to provide extended mechanical ventilation, the patient will literally asphyxiate.
The sheer clinical risk hiding in a single molecular variance is just staggering. I mean, it transforms the concept of biochemistry from something you cram for on a board exam into a very real checklist before surgery.
Absolutely.
It's the physiological justification for why anesthesiologists take those deep family histories about adverse reactions to anesthesia or even run lab assays to test plasma cholinesterase activity beforehand.
You're mapping the patient's individual biochemical blueprint before you intentionally alter it.
So true. But, we've been talking about the consequences of enzymes that circulate in the blood failing to do their jobs. The dynamic shifts entirely when we look at enzymes that belong locked inside the cell cytoplasm suddenly showing up in the bloodstream.
Yes. We're moving into the realm of diagnostic biomarkers.
Yes.
So when tissue undergoes ischemia, which is a restriction of blood supply that causes a shortage of oxygen, the cells cannot produce enough ATP to maintain their membrane ion pumps.
And when those pumps fail, water rushes into the cell swells, and eventually the plasma membrane physically ruptures.
Exactly. It bursts open. All of the intracellular contents, including structural proteins and metabolic enzymes, spill out into the interstitial space and eventually wash into the systemic circulation.
And the textbook spends a lot of time on how this exact mechanism is utilized to diagnose an acute myocardial infarction, a heart attack. The cardiac cells tear open and dump their specific proteins into the blood. But the detection of these proteins is heavily dependent on the physical size of the molecules involved.
Size and solubility completely dictate the timeline of the diagnostic window. We measure the size of these macromolecules in Daltons. When a cardiac muscle cell bursts, the speed at which a protein diffuses through the cellular debris and enters the capillaries is basically inversely proportional to its mass in Daltons.
So it's literally just a physical size issue. The cell membrane breaks, but the internal contents don't just instantly vanish into the bloodstream. It's almost like, well, if a massive cargo ship sinks.
I like this analogy.
Yeah, the small, lightweight, buoyant cargo floats away and hits the surface immediately. But the massive, heavy machinery that's strapped to the lower decks, that takes days to break loose and float up.
That is a highly functional way to visualize the kinetics. The light cargo in this scenario is myoglobin. It's an oxygen-binding protein with a molecular weight of only 17,000 daltons.
That's tiny.
Incredibly small and highly water-soluble. So when the cardiac cell ruptures, myoglobin diffuses out almost instantly. An ER physician will see elevated myoglobin levels in the patient's blood within just 6 hours of the initial infarction.
But because it's so small, the kidneys also filter it out of the blood extremely quickly, right? So if you test a patient 2 days later, the myoglobin is probably already gone.
Which necessitates looking for the progressively heavier cargo. Creatine kinase, or CK, weighs in at 80,000 daltons. Aspartate transaminase, or AST, is 93,000 daltons.
Okay, so much bigger.
Right. Their larger physical mass means they take longer to navigate the interstitial space, usually peaking in the blood around 24 hours after the event.
And then the heaviest machinery would be lactate dehydrogenase, or LDH.
LDH is a massive tetrameric enzyme boasting a molecular weight of 135,000 daltons. Because of its sheer bulk, it diffuses incredibly slowly out of the necrotic heart tissue. And furthermore, its large size prevents it from being rapidly filtered by the kidneys.
Right.
Consequently, LDH levels will remain elevated in the patient's plasma for at least a week following the heart attack.
We have to factor in troponin as well, since that's the current gold standard for this diagnosis. Based on the Meisenberg and Simmons text, troponin seems to operate under like a dual mechanism. It's not just about mass, it's about structural binding.
Troponin is unique. The cardiac isoforms of the troponin subunits range from about 18,000 to 37,000 daltons, so they aren't exceptionally large.
They're pretty light cargo.
Right. However, only about 5% of the cell's troponin is dissolved freely in the cytoplasm. The other 95% is structurally anchored to the contractile filaments of the muscle.
Oh, wow. So when the cell bursts, the 5% that was floating free washes out rapidly, which creates that initial spike in the blood tests around 24 hours. But the remaining 95% is literally tied down to the wreckage of the cell.
It remains anchored until the necrotic heart tissue physically degrades over the following 1 to 2 weeks. As the structural filaments slowly break down, the bound troponin is gradually released into the bloodstream. This slow, continuous release provides a sustained diagnostic marker that can confirm a myocardial infarction days after the acute event has passed.
Which perfectly highlights why a physician must understand the molecular weight and the structural biology of these markers. I mean, if a patient presents with a history of crushing chest pain 3 days prior, ordering a myoglobin test is clinically useless.
Completely useless.
The timeline requires testing for the slow-diffusing LDH or the structurally anchored troponin.
It demands an understanding of the mechanical reality of the tissue damage.
Diagnosing the damage is one challenge, obviously, but treating the resulting inflammation introduces an entirely different web of physiological chemistry. The textbook outlines this sobering example of how our attempts to rationally engineer around biological pathways can backfire catastrophically.
Yes.
Let's dig into the COX-2 inhibitors and the fallout surrounding drugs like Vioxx.
The pharmacological history here is a stark lesson in systemic biology. Traditional nonsteroidal anti-inflammatory drugs, or NSAIDs like aspirin and ibuprofen, they exert their effects by inhibiting the enzyme cyclooxygenase, or COX.
Right, and the suppression of COX reduces the synthesis of pro-inflammatory prostaglandins, which basically reduces pain and swelling.
Exactly. But the human body utilizes different isoforms of this enzyme. Traditional NSAIDs inhibit COX-1, which is constitutively expressed in many tissues, particularly the gastric mucosa. In the stomach, COX-1 produces prostaglandin E, which functions to reduce acid secretion and promote a thick, protective mucus lining.
So when a patient takes a traditional NSAI chronically, the inhibition of COX-1 strips away that protective gastric mucus, leaving the stomach wall highly vulnerable to its own acid.
Yeah, and this commonly results in severe gastritis and bleeding peptic ulcers. The pharmaceutical industry recognized this side effect and sought a highly targeted solution. They discovered COX-2, an isoform of the enzyme that is primarily induced at sites of inflammation.
And the logic there seems structurally sound, right? If you design a drug that selectively inhibits COX-2, you can shut down the inflammation in the joints while leaving the COX-1 in the stomach completely alone.
The protective mucus remains intact.
Yeah, and this led to the development of selective COX-2 inhibitors like rofecoxib, which was marketed as Vioxx.
The clinical trials confirmed the theory regarding the gastrointestinal tract. The incidence of ulcers dropped significantly. However, the selective inhibition ignored a critical physiological role that COX-2 plays elsewhere in the body. Inflammatory cytokines induce the expression of KOX2 inside atherosclerotic lesions. Those are the fatty plaques built up inside arterial walls.
And what is the specific biochemical output of KOX2 inside those plaques?
The endothelial cells lining the vessels use COX2 to synthesize a molecule called prostacyclin. Prostacyclin is a potent vasodilator, and critically, it strongly inhibits platelet aggregation.
Oh.
Yeah, it acts as a localized biochemical brake, preventing blood clots from forming on the surface of the plaque.
Wait, so by selectively blocking COX2 systemically, the drugs inadvertently shut down the production of prostacyclin in the heart's blood vessels.
Exactly.
You literally remove the biochemical brakes on blood clotting right at the site of a vulnerable plaque.
And we have to look at the secondary effect. While prostacyclin production was halted, the selective drugs did not inhibit COX1. Platelets rely entirely on COX1 to synthesize thromboxane, a molecule that actively promotes clotting and vasoconstriction.
Yikes. So the selective inhibition created a massively unbalanced prothrombotic environment.
The platelets activate, they clump together, and suddenly a massive thrombus forms over the plaque. Blood flow to the heart muscle stops. The tissue becomes ischemic, the cells rupture, and we are back to the myocardial infarction we just discussed.
That's awful. In attempting to rationally engineer a safer painkiller, they accidentally triggered acute heart attacks, forcing the withdrawal of Vioxx from the market. I mean, it really demonstrates the profound interconnectedness of these pathways. You cannot isolate a single cellular mechanism without accounting for the systemic ripple effects.
You can't. And that concept of systemic ripple effects requires us to examine how a cell actually coordinates all of these competing pathways. I mean, how does a single cell decide when to synthesize proteins, when to conserve energy, or when to break down its own organelles?
And the central command node for that decision-making process is the mTOR pathway.
mTOR, which stands for the mechanistic target of rapamycin. The text positions this as the master regulatory switch of cellular metabolism.
It's basically an intricate sensory hub.
It is. mTOR exists within two distinct multi-protein complexes, mTORC1 and mTORC2, and each is physically localized to different areas of the cell to sense different environmental cues. mTORC1 primarily physically assembles on the membrane of the lysosome.
The lysosome being the cell's internal recycling center, right? Where degraded proteins are broken down into raw amino acids.
Precisely why mTORC1 is stationed there. It is positioned to directly monitor the availability of intracellular amino acids. If amino acids are abundant, mTORC1 is primed. Meanwhile, mTORC2 localizes near the plasma membrane, where it can rapidly detect extracellular growth factors and hormonal signals, primarily insulin.
So, when you consume a heavy meal, insulin levels spike in the blood, and amino acids flood into the cells. The mTOR complexes detect both the extracellular funding and the intracellular building materials, and the switch flips to the active state.
And activation of mTOR triggers a massive shift toward anabolic metabolism. It aggressively stimulates the transcription and translation of new proteins, the synthesis of structural lipids, and ribosome biogenesis. The cell is literally commanded to grow and divide.
Wow.
Concurrently, active mTOR heavily phosphorylates and inhibits the proteins responsible for autophagy.
Autophagy is that survival mechanism where a starving cell will literally digest its own damaged organelles to harvest energy, right?
Yes.
So mTOR acts as the ultimate biological general contractor. When the insulin and nutrients arrive, it hires the construction crews to build and actively fires the demolition crews to prevent them from tearing down the new structures.
It's a great analogy.
Yeah.
And the clinical relevance emerges when this master switch is permanently jammed in the on position. Hyperactive mTOR signaling is a primary driver in numerous malignancies.
Okay.
Exactly. Tumor cells frequently acquire mutations that render the mTOR pathway oblivious to nutrient deprivation or a lack of insulin. The tumor cell acts as if it is constantly flooded with growth signals, driving reckless, uncontrolled proliferation and lipid production, entirely bypassing the body's natural metabolic constraints.
The tumor essentially hijacks the pathway designed to rebuild tissue after a meal and weaponizes it for infinite growth.
It reinforces the fragility of the balance we discussed at the very beginning regarding ATP and synthetic pathways.
We have covered an immense amount of physiological chemistry today. I mean, we started with the basic balance of anabolic and catabolic pathways fueled by the coiled spring energy of ATP and how the failure of that balance leads to toxic storage diseases.
Right.
We explored the genetic variants of plasma cholinesterase, transforming a standard dose of succinylcholine into a lethal paralytic.
We tracked the timeline of ischemia, measuring the diffusion of biomarkers like myoglobin and massive molecules like LDH based on their Daltons to diagnose heart attacks.
We dissected the tragedy of rational drug design with COX2 inhibitors eliminating the prostacyclin brakes on blood clotting. And finally, we mapped the sensory complexes of MTR, the master switch of cellular growth.
As promised, we want to ensure these concepts actually stick for you. So here's a quick review exercise for you listening. Think back to our discussion on molecular weight and cellular rupture. You are an ER physician. A patient arrives complaining of severe chest pain that they state unequivocally began 4 days ago. If you can only order one blood test to confirm a myocardial infarction, do you test for myoglobin or lactate dehydrogenase?
Oh, that's a good one.
The clinical choice is lactate dehydrogenase or LDH. Myoglobin at only 17,000 Daltons is highly soluble and clears through the renal system within 24 to 48 hours. LDH, weighing 135,000 Daltons, takes significantly longer to diffuse out of the necrotic tissue and clear the body, making it reliable for diagnosing an event that occurred 4 days prior.
It all comes back to the physical reality of the molecules.
It always does. And I want to leave you with a final thought to explore on your own. We've seen how a silent variation in just one enzyme dictates whether a surgical drug is safe or lethal, and how adjusting an anti-inflammatory pathway alters blood clotting. Considering that every human possesses a vastly unique array of these enzymatic variants, how far away are we from a medical paradigm where receiving a prescription without first mapping your entire personal biochemical enzyme profile is considered malpractice?
Wow. It really redefines the concept of personalized medicine. The human body is this shifting, dynamic web of physiological chemistry. Every single intervention creates a systemic ripple, and mapping those currents is the only way to navigate the complexity. Thanks for joining us, and we'll catch you on the next deep dive.